This morning, I'd like to talk a little bit about moisture management in power transformers. And my focus today is specifically on oil-filled transformers. And just kind of as an introduction, before the pandemic, it wasn't unusual to be able to order a new transformer and expect somewhere around a 38-week delivery. Well, now with the supply chain issues that we're facing in the country, that's more like 38 months. And the problem is between the time you have to order a new transformer because your asset is aging out, you just don't know what's in store. The average transformer in the US now is about 38 years old, with 70% of those transformers being older than 25 years. And that is well beyond the life expectancy of their original manufacturing. So one of the things I think that is most important is that we do everything we can to try and maintain these assets, these critical assets, either before ordering a new or, at this point, some of the manufacturers aren't even taking orders. It's getting so bad. So we're in a very difficult situation. So one of the things that we have to ask ourselves is what is it we can do to help protect our assets? There's a number of things we can do. We can certainly make sure that our protective relaying is in place to make sure that we account for any transients that may come and cause damage, mechanical damage to the transformer itself. But what I'd like to talk to you today is excessive moisture. Two things that we know that can greatly affect the life cycle of a transformer and its insulation is excessive moisture and heat. Now, excessive moisture, what I'd like to talk about is a couple of things. We want to talk about what the effects of excessive moisture are, where moisture comes from, how we detect and determine the moisture content inside the transformer. And we're talking about the insulation system, and then some things that we could possibly do to mitigate this problem. When we talk about diagnostic testing of power transformers, there are three basic investigative categories. You have your dielectric, you have your thermal, and then you have your mechanical. And what I have here, of course, is a list of typical tests and diagnostics tests that we do on a transformer to check the health. For dielectric, we're talking about the insulation, okay, and we typically start with an oil screen or a DGA analysis. We do things like power factor or tangent delta, as they say over in Europe. And then another diagnostic test we want to talk about today is dynamic frequency response. And you can see that whether you have a mechanical, thermal, or dielectric category in which you're going to investigate the health of the transformer, some of them do overlap in certain areas. So, there's basically three types of transformer failures. You have electrical failures, you have mechanical failures, and then what we're going to talk about today are insulation failures. So one of the biggest concerns surrounding life extension of power transformers is the health of the insulating materials. Transformer insulation typically consists of liquid like mineral oil and solid insulation made up of pressboard, polymers, or resins. And moisture content in any of these insulation components have an exponential life on the effect of the life expectancy of this device. Okay, so where does moisture come from? Well, moisture can come from a number of different areas, and first and foremost, it can be present during the manufacturing or final assembly process. So it's important when you take delivery of a brand new asset that you know that it has been properly dried out, either in a vapor phase chamber, which is typically done at the manufacturing site before they go ahead and deliver it to you. And then also you can have an outside influence like leaky gaskets or on bushings or radiators, or it can happen during a bushing change out. If you've had a bushing failure or you need to change out bushings, that process can easily allow for moisture to become, to ingress into the tank itself. So it's important to do this carefully. Now, it can also come from outside humidity? Well, it's interesting. I was in Colorado at one point in time and doing a presentation similar to this, and somebody raised their hand from the utility and said, you know, we have a really dry relative humidity out here. We really don't believe this is an issue. Well, one of the things that you have to be cognizant of is the fact that moisture can come from the natural aging of the insulation itself. And this is very important to understand. So how does this happen? Well, what happens is as the cellulose material in the paper in the transformer itself starts to deteriorate, the resin bonds will start breaking apart. And chemically what happens is that the byproduct of these resin bonds breaking down happens to be moisture. And in insulation itself, we refer to the term of degree of polymerization, and that is the actual strength of the resin bonds in the insulation itself. A brand new transformer will typically have a DP rating of around 1800. Now, as the cellulose starts to age and it degenerates, you know, at the end of its life cycle, we're probably talking about a degree of polymerization of about 200 to 300. And the breakdown in this process contributes to moisture. And the older it gets, it kind of compounds itself. But you know, when you split these change by water molecules, and that'll reduce the mechanical force, you know, that the insulation can withstand. So that's important to know. Even in if you never expose the insulating fluids to outside air, just the natural aging of the insulation will create moisture. Okay, now, what is the effects of moisture content? Well, the insulation life expectancy depends on two factors: operating temperature and moisture content. You can see that in this graph right here. On this bottom axis, we have the operating temperature and then the life expectancy. So there is the combination of the both. And typically at this point, a lot of utilities will run their transformers as pedal to the metal. You know, we're at full rating in terms of the load. And the higher the load, the higher the operating temperature. You know, and overheating, that can be a result of poor cooling systems, or even operating conditions such as volts per hertz that we see sometimes close to generating facilities on GSUs. Excessive moisture in combination with the operating temperature greatly reduces the life expectancy. And you can see here on this graph, this is your percentage of moisture in the insulation, and this is your operating temperature. So combined, okay, we're talking about serious conditions. Now, if we talk about brand new transformers, and this is kind of interesting, IEEE, the C57106, this is the guide for acceptance and maintenance of insulating mineral oil in electrical equipment. They say that for new transformers, okay, for the smaller 500 kV or less, we want to have about 0.5% by weight in terms of moisture content. As you get into the larger transformers, or I'm sorry, the smaller transformers are 0.8, the largers are 0.5. So if we take an example, let's say we're looking at a fairly large transformer, 450 MVA, two-winding transformer, 245 to 20 kV, weighs about 250 tons. And that's the core and the coils are about 125 tons, of which 25 tons is actually cellulose. Okay, at 2% water, there's 500 kilograms or 132 US gallons of water in the insulation itself. So to achieve the recommendation of getting down to 0.5 moisture content, we'd have to extract 99 gallons of water. Okay, so that just kind of gives you some kind of correlation of what percentages of moisture content equate to in terms of the actual moisture itself. Now, why is moisture bad? Well, for a couple of reasons. Number one, and first and foremost, it lowers the bubbling point inside the transformer. And when you do this, this can begin to create voids in the insulation. And this results in partial discharge. That's the first indication that you're starting to get an insulation breakdown. Now, the partial discharge can actually lead to excessive deterioration of the insulating paper and damage to the insulation, unfortunately, once it gets to a certain point, is irreversible. There's really nothing you can do about it. So it's auto-acceleratory. That means that the worse it gets, the more moisture it starts to correct. So the point I'd like to make here is that the sooner you address moisture issues in the transformer, the more chances you have for better life extension of that asset. So if we look deep into this, the moisture-induced dielectric breakdown, there's a kind of a chain of events. So it embeds in the voids of the paper, causing the partial discharge. That will cause some carbonization, and that will cause a treeing effect that you can see in this picture right here. And then eventual treeing causes the breakdown of the insulation, and you can kind of get an indication right here. This is definitely a picture of a moisture-related issue. So here's a couple of pictures of severe breakdown of paper insulation. And again, this kind of deterioration is catastrophic. It is irreversible. It can't really be mitigated. It's gone too far. So how do we measure the amount of moisture that's in the insulation system itself? Well, we know that, we can start with, of course, our power factor or our tan delta system, okay, or tangent delta measurements. We know that tan delta measurements are sensitive to aging. They're also sensitive to moisture and contamination. And a power factor test is definitely done. It can recognize changes from previous measurements, and we can eliminate outside factors as contributing variables. And this is a common test along with your dissolved gas analysis. So what are the shortcomings? Well, it kind of represents the average condition of the total insulation system under test. You don't know if it's going to be a general and uniform deterioration, or if it's a severe localized area of deterioration. We just don't know. Now, in terms of moisture, okay, your CHL measurements can show a slight elevation at 60 hertz. But the problem is it's impossible to differentiate and characterize losses, which may indicate moisture, could be aging, contamination, oil conductivity, or some combination thereof. So what can we do in our power factor test to take a look at what could be possible conductive losses? Well, we know in the industry that rather than just doing a standard 60 hertz power factor test, we now have the capability to extend the frequency range of that measurement. And this would take only a few more minutes to perform, and provide some additional information to reveal some what we call blind spots. And when you do a power factor measurement at a lower frequency range below the 60 hertz, this puts an emphasis on conductive losses in the insulation. So what we see here, and you'll see your three typical power factor measurements, that the lower values of power factor indicate that conductive losses are negligible. In other words, if you had a moisture issue, you would not see these types of results. Okay, with a reasonable temperature reading of, let's say, 10 to 30 degrees C and an assumption of low oil conductivity is present, that suggests that excessive moisture in all instances probably isn't there. And if that coincides with your oil screen results, you can be pretty confident that you don't have a moisture issue in the transformer itself. And this is actually a case study that we did on a number of different transformers. So right here, if you see your power factor measurements lower than the values lower than the 60 hertz or 50 hertz nominal, that's a transformer with dry winding insulation. You can feel pretty confident. Now, on the other hand, if you have higher values of power factor before the 60 hertz, that is an indication you've got possible conductive losses. And conductive losses can be sludge or furans or inert furans, or but it also could be moisture. So that should be a red flag right away. Okay, so here's a case study we did with two similar transformers, transformer A and B, and we did a CHL measurement here, and you can see that They're both, at about 0.4, slightly elevated, but maybe not a cause for concern. So if we extend the frequency range, you can see that transformer A has a higher indication of conductive losses than transformer B. Okay, so what does that mean? Well, if we do what's called a dynamic frequency response measurement, we'll get into this a little bit later on, we determined that in transformer B, we only had a 1% moisture content. And that is certainly acceptable. I mean, the acceptable ranges, according to IEEE, is typically somewhere around 4% or higher, or maybe 3.8, and depends on the size and type of the transformer. But 1% water content is not certainly in an acceptable range. This particular transformer A, had a 3.4% water content, and that is getting up to that critical stage, depending on its operating temperature, as we said before. So if we graph this out on what we call the Lungard chart, you can see that high temperature and moisture content will dramatically affect the mechanical strength of the paper insulation. So transformer A with a lower moisture content would have a life expectancy much lower than the dry. So this is our transformer, okay, at 3.4% in terms of its life expectancy and operating temperature, which was at 70 degrees C versus 100 years on a 1%. So this is all good documented information that we've gone on. So what's the concern with where is the water? Well, and this is important to understand, especially if you rely on pulling oil samples and doing an oil screen for this type of test, because during normal operation and at different loads and temperature, the water moves back and forth between the oil and the cellulose. Okay, the portion of moisture to oil versus cellulose depends on the transformer's operating temperature. So if you are going to do dielectric testing on your transformer and diagnostic testing, you take the transformer offline. The transformer starts to cool down naturally. But as the transformer cools down, the moisture goes from the oil back into the insulation when a transformer comes alive. Now, this creates an issue for true moisture measurements from an oil sample. And there are a couple of issues surrounding what we call the applying equilibrium curves. So unfortunately, this is the most common method of measuring moisture content in the oil. Measuring moisture oil levels in oil is absolutely the most common. And of course, you can sample the oil under service conditions. And then we do a dew, what's called a dew point, or a measurement of water content through a Karl Fischer titration. And that's done usually under laboratory conditions. And that is deriving moisture via deriving or trying to estimate the content of moisture in the oil, trying to determine what it is in the paper insulation, using what they call equilibrium curves. And this was established by IEEE many years ago. So if you record the oil temperature when you take the sample, you can apply that to make a reference to what would typically be in the insulation. But there's a couple of problems with that. Number one is if your sample gets compromised and exposed to any kind of atmospheric conditions between the drawing of the sample and the laboratory analysis, it can get, it can give you unpredictable errors. The equilibrium diagrams are only valid under certain conditions, depending on the temperature of the transformer. One of the issues that you also have is that if you're recording your top oil temperature, as you draw the sample through the ball valve of your transformer, that's going to cool the oil coming into play. So that could also distort your results. We had a situation where we took 5 different oil samples at the exact same time from the same transformer, sent them off to 5 different laboratories. And the moisture analysis the ppm analysis came back with ranges that were not very consistent. So one thing that you could certainly do is just be very careful in drawing your samples and making sure there's no contamination on the way to the lab as it's being measured. Okay, there's some other methods as well, and this is becoming more popular. Okay, and we'll see, especially with new transformers, where they're doing continuous online monitoring systems. And the technology here is actually starting to get much better. And this, the good news is that you have continuous monitoring of moisture content, and this is actually a saturation point, and it disregards the condition of the oil. It doesn't require any additional test equipment, and you can, of course, set it for alarms if you happen to run into a situation where moisture is starting to get too high. The problem is, and I know this technology is improving, and it may be, coming down in terms of the relative cost, but it is typically expensive to do, and it's done during the manufacturing process. They take these capacitive probes and they actually embed them into the insulation, but it measures the saturation levels of the insulation, not the actual water content itself. Well, what can happen? Well, you can get sensor failure, and I'm not sure if you could actually correct that without detanking the transformer and replacing it. Maybe the calibration is a bit hard to verify, and as I said again, this technology is improving over and over, and it is relatively new to the industry, and I'm not sure that at this point that it's applicable to existing assets. Okay, so one of the methods that IEEE is recommending, and this is some proven technology, and I know that some people may not have a lot of trust in this, but this is called dielectric frequency response, or DFR. And the first instrument for DFR was actually manufactured back in 1995, but since then, numerous evaluations of the technology have been performed at different international projects and reports to actually define the modeling that's built into this. So what is a DFR test? Well, that's a capacitance and dissipation power factor measurement at a very wide frequency range. And what this does is and this is a low voltage, very non-invasive test. It has to be done offline, of course, which also gives us quite a few challenges, especially with the heat that we're seeing this summer across North America. Nobody wants to take their large transformers offline. But unfortunately, if you're going to do good maintenance testing and you don't have a complete monitoring system on the transformer, this is going to be quite necessary. But using DFR for moisture determination is based on a comparisons of the transformer's dielectric response to model dielectric responses that they did under laboratory conditions. So what happens is you actually are measuring these wide frequency range of dielectric of the response and equating the results to what was determined under laboratory conditions using a Karl Fischer titration. And under laboratory conditions, meaning that you knew what the exact percentage of moisture in the insulation was and could compare that to how that responded to the particular curve that's going to be a result of this test. But it is non-invasive and it is done offline. The dissipation measurement of solid insulation is what you're looking at. This is disregarding what's in the oil. This is what's in the insulation, and that's where our big concern is. The interpretation of the measured curve relies on the sampling database that was built into the software that actually gives you your measured results. And this is a proven interpretation scheme. I mean, this is all part of IEEE PC 57162 and IEC standards 6422. The results are temperature sensitive, so it is important to record your temperature results at that time. And they actually use this under drying conditions for brand new transformers. A lot of the factories have taken this method to make sure that you're getting delivery of dry insulation. Okay, so this is kind of a connection diagram. It's actually quite it's a loaded device where you will actually tie in your bushings together to simulate the load, and then you have your low voltage cable along with a guard to keep any noise, if you're in a noisy substation, from interfering with the test and the test results. So we're just going to inject the frequency signal at around 200 volts on the high side and measure on the low side, and come up with our measurements. And this is what you'll see as a result. And you'll see the characteristic of the curves of the measurements at the very wide frequency range here. And you can see that the higher your influence is here, the higher the moisture content. The good news is that the software that comes with these devices actually does this calculation for you, and it will tell you. But again, very important because it is a temperature sensitive measurement to actually apply those measurements into the test parameters before you get your results. Okay, so what if you determine you have a moisture problem? Well, there's a number of things that you can do, and there are different methods for drying that are actually summarized in two different ways. Drying the insulation by drying the oil, okay, which is typically what we've seen in North America, or drying the insulation, of course, by putting in a vapor phase chamber. But this certainly isn't something that's practical for aged transformers. Basically, if you were going to put it in a vapor phase chamber, you'd have to detank it, send it back to the factory, and then do your vapor phase process there. The problem with trying to do that on an aged transformer is it can actually cause more problems that it can solve. You can actually destroy the older insulation by trying to do this after the transformer's been in service for many years. So what people do is that they'll actually, you can perform a vacuum and heat, and you can use hot oil spray drying, you can bring up a truck and do an oil exchange. But the problem with this is that you're pulling the moisture out of the oil and not the insulation. And if the transformer is offline, remember that moisture's gone from the oil back into the insulation. So you're maybe kind of putting doing your best to dry out the insulation using the oil. So we'll heat the oil up. We'll do a hot oil spray to try and pull that moisture out of the insulation. But again, the effectiveness and the cost of doing this, you have to have the transformer offline during this process, and that's a problem for a lot of utilities. And it's not all that expensive, all that effective, or not as effective as we'd like the drying process to be. So the other is that we can dry the oil again with, cellulose filters, molecular sieves, cold traps, combined with oil regeneration and degassing, many different ways. But what we're doing is we're addressing the moisture that's in the oil. Well, one of the methods that we've found, and we found this to be quite effective, is an online drying method for transformers. So there are devices that you can get. They're high volume, high capacity filtration systems that can be done during the online process. In other words, you can have your transformer up and running during this drying out process of the oil. Now, how does that help improve the process? Well, if your transformer is online and it's loaded down, that means you're going to be operating at a higher temperature, okay? Which means that at an operating temperature, you're more at an equilibrium state where your moisture in the insulation equals what's in the oil. So as we dry the oil under load, okay, what this does is it starts to pull the moisture out of the insulation to maintain equilibrium. And this is actually quite a benefit to be able to use these types of systems and to be more effective in pulling out the moisture. So basically, these online dryers, they use either a low volume or a high volume pump to actually extract the oil, removing the water and removing the moisture from the oil while it's online, and it doesn't really, it's not going to drop your oil levels down below a critical level, especially if you have a conservator tank. It really doesn't use that much, but this has been proven to be quite effective. And some of them actually, I know that the ones that we read actually have a self-drying system where the filters will actually self-dry themselves. So it's kind of a hands-off process. And this is, again, this was a recommended method from IEEE C57140. Very useful for field moisture reduction on non-vacuum rated transformers. Okay, so one of the other benefits of using a system like this is it will actually perform a degassing as well. So, two instances, two separate problems that we can have in transformers. We can have excessive levels of gassing due to various conditions, or a moisture problem. Now, what's important to know that if you do want to go through a degassing cycle in the transformer, it's very, very important to know what is causing that gassing condition. So, if we have fixed an issue or repaired a problem and you still have a high level of gas in your transformer oil, a unit such as this can remove the gas. We had a situation where a utility had ordered a new batch of, I think maybe a half a dozen or so auxiliary transformers for their power plant. And one of these transformers started to gas almost immediately as it was put into service. So they took it offline, they sent it back to the factory to be reworked. It had been reworked, and they put it back in service, and the gassing continued. And the gassing it was showing was hydrogen, oxygen, nitrogen, which really is an indication that you've got some kind of arcing and sparking going on inside the transformer itself, causing this condition. Well, the customer was quite upset with the manufacturer and said, look, we want this thing replaced. We've tried to have it repaired at one particular point, and it was not effective. And so the problem, again, we have with lead times was that it was about 6 to 7 months out before then. So they had to keep the transformer online. It was a critical asset. And what they did was they put this filtration system in place. And you can see here that these were the extremely high levels of oxygen, nitrogen, and methane. And they put this process in place, and it did a rather good job at keeping the combustible levels of gas in check while the new transformer was being replaced. So, in conclusion, we'll certainly have time for questions, is that we know that moisture in the insulation system of a power transformer can definitely lead to premature failure. And this certainly we want to avoid at all costs. Excessive loading, such as heat, can further accelerate the process. It's like getting a new car. If you buy a new car, it's expected to last a certain amount of time. Well, if you're driving pedal to the metal, and abusing it, it's not going to last quite as long, would it? And it's the same thing with the power transformer. There's a number of different ways to determine moisture content, but I would recommend that DFR is something you'd want to consider if you truly want to know how much moisture is in that insulation. And drying methods can certainly vary, but if you want to reduce cost and eliminate downtime on your transformer itself, this online process should be considered. So thanks so much for your attention and listening, and we'll take whatever questions that you may have with regards to the presentation.
Okay, thanks very much, Drew. And yeah, we have several questions. First one, what temperature is considered excessive heat? Does ambient temperature play a factor?
Ambient temperature typically does not, unless you have a fairly inadequate cooling system, such as your radiator systems. But yes, ambient temperature can play a heat, because what happens is when you have a lot of ambient temperature that's running very hot, that means your loads are going to be high, typically higher. You've got air conditioning, you've got all these conditions that make the loading that much higher. And this is one of the problems that we're facing with right now, because your regular maintenance in substations right now are being kind of put off, because the loads are so high based on the temperatures, extremely high temperatures across the country. But basically, your operating temperature has to do with the loading capacity of the transformer itself. So this is important to know, because if you're overloading a transformer and that is loading it beyond its rating, that's going to cause the excessive heating.
Okay, what is the best process to dry out the transformer?
Well, we recommend these online drying systems. They're not invasive. They are very effective, and you can keep the transformer up and running while the drying process is being conducted. And a nice thing to know is that it does have a self-monitoring system, but it also comes equipped with things like a network connection, or even has cell phone modem attached to it, so you can get a daily report of the progress. The thing that concerns people a lot is, well, what happens if a hose bursts, or something goes wrong with the process and nobody's there? If there is a problem with the system, and in terms of its integrity, it will shut itself down, close all its valves, and then send an alert.
Okay, thanks. Next question. What is the percentage of installed transformers in the United States that have been identified as having a moisture issue based on annual liquid sampling results?
Well, that's a good question, and I don't have the answer right offhand. But I can tell you this. First of all, I would say that the percentage of transformers with a moisture condition is probably more unknown than it is known. So even the best statistics to tell you that there's a moisture issue may not be entirely accurate. I can say this, that if you look at an individual utility itself, a lot of it depends on the age of the transformer, the average age, and the way it's designed. The design has a big influence on the ingress of moisture, because if you have a free breathing conservator and your desiccant isn't very effective, you can have moisture ingress. And this was a problem that Duke Energy had a number of years ago. They had free breathing conservators on a lot of old transformers, and the desiccants weren't well maintained, and they had a huge moisture issue. In fact, they had a moisture issue in one particular transformer. I can remember seeing this at a TechCon conference. It was so bad that the actual transformer blew up, in the seam that blew apart in the tank, some guy was actually standing in. Luckily, it didn't catch fire, but it was a catastrophic situation. But in terms of percentages across the country of those that are at a critical level, I don't have statistics on, but it's a very good question, and something that would be interesting to try and determine.
Okay, next one. There is a trend of running a short heat run to get rid of partial discharge, which appears during FAT. If it works, could it be that the problem was not solved but shifted to another time on site?
Yes, especially when you start putting a load on a transformer, and a continuous load. Sometimes the problem with a factory acceptance test is if you use a large load bank to simulate load, it's only there for a certain period of time. And this was the problem that we saw at the utility with the aux transformer. Passed the factory acceptance test, even passed it after they tried to do a repair on it. But somewhere in that tank was a loose ground strap or something, causing that arcing and sparking to get that, to cause an issue in the transformer itself. So yeah, a lot of times some of the factory, some of the bad manufacturing isn't present always visible until you actually have a continuous load.
Okay, next one. Any considerations from manufacturers to deal with reverse power of connected distributed energy resources?
Yeah, so it's a hot topic right now. And it's not one of the committees I'm on, unfortunately, but reverse power is a concern in DER situations. And one of the things that we do to get around that, and this is more of a problem when you get deep into the distribution network, things such as voltage regulators. And they're starting to consider designing power transformers also to be able to run in a reverse power condition. But it's the sensing of the reverse power condition that's important. And this is basically done with your load tap changer controls. Because with a voltage regulator, what are you supposed to do in terms of regulating the power when it's running in reverse? And there's a number of things you can do in terms of being a load tap changer control. You can say, well, I'm just going to run to neutral and just sit there. Or you can just maintain the tap that it's on. That's kind of the deer in the headlights thing. But there are opportunities where you can actually determine at the load tap changer control that you do have a reverse power condition. And they do this by running the taps and seeing the effects of the voltage and saying, okay, I'm running in reverse power, and then switch to a reverse power mode. So this is something that if you're in distribution and you're having DER voltage control problems, something you definitely want to look at. And there are certain manufacturers out there that are working on resolving this issue.
Okay, what is the best time of the year to take oil samples from a transformer, especially from moisture point of view?
Well, the best time is when it's convenient for you to take your transformer offline. And that's important. And this is a problem that we're seeing right now. Because of the excessive load that the excessive heat throughout the country is causing. I was in a working group meeting on Monday this week, and we were talking about, I'm on a working group that's dealing with the setting standards for transformer monitoring. And a comment was made by one of the members that's saying nobody's taking their transformer offline. Now, keep in mind that ultimately you can take an oil sample while the transformer is online, but it's certainly not recommended. And the reason it's not recommended is the catastrophic event of having a winding failure or something internal to the transformer happen while you're taking that sample can be very, very dangerous. So it's not recommended. So time of year is really relative to when it's applicable to be able to take your transformer offline.
Okay, just a couple more questions. Are there any statistics on how many transformers have failed due to moisture?
Well, and that's a really good question. Because, and yes, I do have those statistics, and anybody's invited to send me an email, and I'll respond to that, because I do have statistics on that for sure. But the problem is, if you have an insulation failure and it's gone too far, it's hard to determine exactly if moisture was a condition, depending on the extremity of the failure. If it was catastrophic, you've kind of passed that point of determining what happened in the insulation. But yes, I do have some statistics on that, and I'll be happy to send that to you. I have a 4-hour presentation on why transformers fail, and there's some really good statistics that go with that presentation. So if you'd like to send me an email, I'll be happy to respond with that information.